Hey there, everybody. Welcome back. Let's take a look at the main topic of this section is the Jacobian. So we're going to start off with a small rectangle in UV. In the last video, we had it going along U equals 0 and B equals 0, and then U equals 1 and B equals 1. Simple square. Here, we're going to have endpoints of U0, V0, and we're going to move delta U and delta V in those coordinates along those axes. So let's just look at how it would, like an example of the mapping. I've got A and B here, side 1, alongside 1, B equals V naught. And let's say it maps over to this blue line curve right here, where B equals V naught. So in the XY region, it's ugly. In the UB region, it's pretty. And S, instead of using 0, we're going to use V naught. And then S4, instead of using U equals 0, we'll use U equals U naught. That maps over here. It's an ugly, again, a curve creates an ugly region. What we're looking at is in blue. And then our vectors are along the points right here. We're going U, V naught, points from U, V naught, or points to A, sorry. R1 is pointing from, this is written funny. Yeah, U is changing along here. So V naught staying the same, U is changing. So it's the vector there. And then R of U naught B, we're going along that vector there. I've labeled them AB and AD because that's our endpoints. So let's just look at how the whole thing would map out. S1, we have the sides of the rectangle. Side 2, U naught, U equals U naught, and we've shifted over, added delta U going this way. So U plus U naught. That's what's staying constant here. So B is changing over here. On side 3, B is constant. U is changing. V is a constant value of V naught, which is the bottom line, plus delta B, the rise up to this line. So that'll be side 3, and then side 4 is back to U equals U naught. And we just map the 4 points with A, B, C, and D, how they turn over into the vectors, okay? And maybe we could write what the vectors look like. So, well, those are points. So I'm just a vector to the points, sorry, not the sides. Okay, so for sufficiently small delta U and delta V, the curve from A to B can be approximated by the vector from A to B. So if we get delta small enough, the distance from A to B in a straight path is approximately the curve. Delta V's got and delta U's got to get really small though. And the same thing for AD and side 4. So AB is the vector from R U naught plus delta U V naught minus R U naught V naught. That's our AB. If we did that as a limit of delta U going to 0 because we wanted it sufficiently small, notice this setup is actually the definition of the derivative of R with respect to U. Okay. Move this down a little bit. There we go. When I take the limit of this vector, remember we got endpoint minus starting point for vectors. So our starting point is U naught V naught in R, and then U naught plus delta U V naught up here. Sorry. U naught V naught is A. B is U naught plus delta U V naught. So that's over here. We have that in our vector. We're subtracting it. And we want delta U to go small. We're doing it as the limit goes to 0. We're actually, what do we have? If we divided by delta U, we would have dr du. So if we multiply this by delta U over the other side, we actually have that. So AB is delta U times dr du. Same thing with AD. AD would be delta V times dr dv. Okay. So let's bring that up on the next page. Take a look at it. I redrew the picture. So we had AB is like this, AD is like that, and it's approximating these curves as they go to 0. The actual area we're looking at is the blue area, but we can make a parallelogram out of it, and we can approximate the area in the blue region with the area in the parallelogram that has sides AB and AD. How do we do that? We take the cross product and the norm of it. So AB was dr du times delta u, and AD is dr dv times delta v. Delta u and delta v are just constants we can factor out. So we have the cross product of dr du and dr dv times delta u delta v. And if I do that, notice the k component 0 because it's just two-dimensional. We just get dx du dy dv minus dx dv dy du. We're taking the norm of that, so it'll just be a value. Okay. This is going to be called the Jacobian. This is for when we're transforming from one set to another. That's how we do it. It's denoted. We use J for Jacobian. The Jacobian of uv is the partial derivatives of x and y with respect to u and v. And it's just a nice little determinant. This can be a pain in the ass to remember. But either remember we go alphabetically along the top and alphabetically downward along the bottom. So x and y and then u and v. And then if you're doing it like this, you're memorizing this, which I don't. I do this every single time. So just remember we got x and y across the top and then u and v on the bottom going down. Our delta A, so our area, our delta A is going to be this Jacobian with the delta U, delta V. Okay. And this is another notation for the Jacobian. We write, this is supposed to represent that. Okay. And so that's going to be our, when we do our U sub, we remember like when we had the 1/2r du and dr, this is like the Jacobian. Okay. So dx partial derivatives of x and y over the partial derivatives of u and v, and it makes a nice little determinant. That's going to be their Jacobian. Next video, we'll see it at work in a couple things. Peace.